assessment. So, speaker is Huining from University at Buffalo State University of New York.
Hello, everyone. I'm Huining. I'm a PhD candidate from University at Buffalo. Today, I'm very happy to present our paper, NeuralGait, Assessing Brain Health Using Your Smartphone. This work is collaborated with University of Rochester Medical Center, Kunshan University, and Case Western Reserve University. As the population ages, preserving the brain health becomes very challenging. In the United States, around 1 million people have Parkinson's disease. Around 0.8 million people have a stroke, and 0.2 million people once suffered from the traumatic brain injury. Timely diagnostics and treatment can help slow or reverse the brain disease progression. However, people are seldom aware of the early signs or progression of the brain disease. Nowadays, many clinical studies have validated the relationship between neural disease and the gait impairment. For example, Parkinson's disease is caused by the death of dopaminergic neurons, so patients may suffer from freezing gait or shuffling gait. Traumatic brain injury changes the cerebral blood flow and pressure, which can lead to lower gait speed and less single-leg stance duration. For the stroke patients, the cerebral circulation is damaged, so they may have relatively preserved arm swing during walking. We can see that gait is an effective behavior biomarker for neural disease. With the advance of maps technology, smartphones can be used to monitor the gait. Inertial sensor-based gait analysis may have two directions. The first one is to extract some temporal gait features, such as swing time, stance time, freeze index. But these features are mainly handcrafted and might miss some inconspicuous but key pathological information. Another direction is to develop data-driven gait feature learning models, such as CNN autoencoder. However, a single model is often dedicated to a single disease detection. So, the high-capacity pathological information hidden in gait is largely unexplored. Now, let's look back to the gait rationale. We know that gait is generated by the coordination of human brain and muscle-skeletal system. In a gait cycle, the behaviors of heel strike and toe off alternatively happen to regulate the swing phase and the stance phase. We can observe that the gait segments in a cycle are affected by each other. So, it is feasible to hypothesize that if a brain disease changes the properties in a certain gait segment, it will influence its relationship with other gait segments. So, our basic idea is to leverage the relationship between different gait segments within a cycle to identify the pathological information. We can borrow the wisdom from NLP to realize our idea. Similar to NLP, gait segment is like a word. Gait cycle is like a sentence. We know that the goal of NLP is to understand the meaning of a sentence by studying the relationship between words. Similar to it, our goal is to identify the pathological patterns hidden in a gait by learning the relationship between gait segments. Now, let's look into some technical details. The first step is gait cycle embedding. We split the gait cycle spectrogram into 14 times 14 patches. On the one hand, we record the geometric information of each patch. On the other hand, we flatten the patch and project it to a space that can characterize the appearance. Then we add the geometric embedding and appearance embedding together to generate the gait cycle embedding. After that, the gait cycle embedding is input to a SelfAttention based module to extract relationship between any two gait patches. We optimize such an extractor by setting the learning task as predicting Parkinson's disease, traumatic brain injury, and health subjects. We know that Parkinson's disease belongs to the neurodegeneration disease. Traumatic brain injury belongs to the structure damage disease. They are from two typical types of neural disorders. So we choose them to train a general relationship extractor. After training, the parameters in the extractor are frozen, which can be used to infer the relationship features for any neural disease. Finally, we fed the gait relation features to a pathological risk estimation network for multi-label brain disease detection. The risk estimation network consists of a shared module and a customer module. The output of each customer module is yes or no for identify each disease. Whenever introduces a new neural disease, we only need to retrain the customer module. To evaluate our system performance, we conduct a clinical study. We recruit more than 900 healthy people and 400 patients with a combination of PD, TBI, or stroke. Among them, 34% are females, and their age ranges from 20 to 78 years old. We ask the users to place a smartphone inside their pocket while working. Finally, we collect around 50,000 samples from healthy people, 20,000 samples from PD patients, 10,000 samples from TBI patients, and 6,000 samples from stroke patients. Our system can achieve around 78% exact matching accuracy for multi-label neural disease classification. For the patients with multiple disease, 65% detection results are completely correct, and 17% are partially correct. To conclude our paper, in this work, we identify that the relationship between different gait segments can be used as a principal cue for multi-label brain disease screening. Our system can achieve around 78% exact accuracy for multi-label disease detection, only use a smartphone. Yeah. Thank you, everyone. I'm happy to take any questions.
Any questions?
Testing. Okay. As we know that FOG symptoms appears at the late stage of Parkinson's disease or any others neural disease, so I would like to know, even though you have great observations that each gait cycles will affect each others, but how can you definitely make sure that your accelerometers readings can help with detecting the neural disease? And the second question is that what's about a single label detection accuracy? Yeah, thank you.
Okay, thank you for this question. Yes, our work is mainly to detect the early signs or the progression of the neural disease, and for the single label accuracy, our work can achieve around 85% accuracy to detect one label disease. And the focus of our work is to detect multiple labels. So we do many work to try to extract some high definition features for the multi-label disease detection. Yeah, thank you.
Okay, thank you.
Yeah.
Okay, let's thank the speaker again. Okay, thanks. Okay, the third talk is behavior modeling for forecasting physical functioning based on multimodal data. It's, well, not just the sensor data, but also